Okay, so welcome to class 17, and the aim of this lecture is basically apply the formalism of StatMech that you might have learned till now to a different class of problems away from ideal gas, where we have already seen how one can calculate the partition function, and from there take the suitable derivatives. From partition function, calculate the free energy, and then take suitable derivatives to get PV equal to nRT and average energy of the system, and get equipartition theorem, and so on and so forth. But those were non-interacting particles. What we're going to discuss today is also non-interacting particles, but at least from on a different class of systems compared to the ideal gas. So that's what the aim of the next 2-3 classes is going to be. All right. So the other thing is there are some more formalism aspects to be discussed. For example, Liouville theorem, virial theorem, and so on and so forth. H theorem, also grand canonical ensemble. But what we're going to do instead is focus on applying the formalism to a few classes of different systems, so that you get a more hands-on feeling for how to use StatMech and what is it useful for over and above the ideal gas. So the question is, let's suppose that you have this formalism which was developed intuitively for the ideal gas. What other phenomena can be understood with this formalism? So that's the broad perspective. To do that, so we shall discuss about some magnetism, magnetic systems, and there is at least two broad classes of systems. So what you could have, so this is a picture from Rife, section 7, figure 7.8.3, which means the chapter 7 and 8 section, and so on and so forth. So what is plotted is the mean magnetic moment per particle. I think this is per particle. Okay. And what is plotted is the magnetic moment per particle. And if you know that, if you can measure the total magnetic moment of the sample, and if you by any chance know how many atoms or molecules are there in the sample, right? Then you can plot the magnetic moment per particle. Alternatively, what you could do is, so let's stick with that. So what has been taken is three classes of samples. One sample is potassium, chromium, alum, and the potassium, chromium, alum, I think is this. The second sample is iron, ammonium, alum, which is this, and the third being gadolinium sulfate octahydrate, and this corresponds to this. And what is important is they have magnetic moments on each atom or molecule, as the case may be, right? And they have different values. So when I'm talking about magnetic moment, I'm really talking about the magnetic moment per atom or per unit of latticite. And that essentially is related to the spin of the system. Now, you might know that if you have done your quantum mechanics 1 or quantum mechanics 2, there's the angular momentum algebra, where you can have one spin, or an electron can also have angular momentum, orbital angular momentum. So finally, per latticite, when you add it up, there is some net angular momentum, right? Which is, I think, called the total spin, and then that can go from minus m minus m, the magnetic quantum number, to plus m. Right. Now, just assume that we're discussing angular momentum, and each of these three samples have different values of the maximum magnetic, they have different spins. I mean, for simplicity, it might be any angular momentum, but just for the simplicity, just assume that we're really talking about the maximum spin, maximum magnetic quantum number that it can take, and these are different for the three samples, right? So the magnetic moment, that the maximum magnetic moment that it can show under application of an external magnetic field H, right, will be different. And these samples, so what is plotted on the x-axis is H versus T. So what you could say that, okay, at fixed T, you could be looking at different magnetic fields. On the other hand, you could fix a particular magnetic field and you could be looking at different temperatures as well. And finally, what has been plotted is basically externally applied magnetic field H, or for the rest of the calculations, I shall also mention it, replace it by B. Uh, so, so that's the external magnetic field by temperature. Now, these samples, when H is 0, show no magnetic moment. Suppose at a particular temperature, we are talking about a particular temperature, but and here the temperatures being considered are relatively low, right? But suppose that at a particular temperature you have a certain you have zero magnetic field, then these samples do not show any magnetic moment. But as you increase the magnetic field, you see that the magnetic moment per lattice site, per spin, if you like, that actually increases. That increases nearly linearly here, but then it goes up and then it saturates to one particular value. On the other hand, if you really talked about, you have applied a magnetic field and keep on increasing the temperature, right? So suppose you have a temperature of whatever, 3 Kelvin, and there you have applied a certain magnetic field, right? But you keep on increasing the temperature. Then again, you will see that the magnetic moment goes to 0. Now, for different samples, there are different maximum magnetic quantum, the largest magnetic quantum number. And in these three cases, they go to three different values of they saturate at different values of the magnetic moment per spin. Okay, so this is, as I said, data from this is a figure from Rive, and this is the paper. And the question is, can we understand how such behavior comes in? So what you macroscopically can measure is the magnetic moment of the sample, right? I do not know how they measure it, but I hope arrange a class given by Sujit Singh, who will tell you the details about that. So I do not know, but suppose the maximum magnetic moment which you see at high value of h by t, for a particular value of t, let's assume a very high magnetic field, whatever 30 into 10 to the power 3 Gauss, but whatever be the units. It shows saturation, and here it shows an increase, even a linear increase here, but then gradually saturates. So can we understand this phenomena using statistical mechanics? What does it mean to understand the phenomena by statistical mechanics? Of course, at the microscopic level, a priori, we do not know what is happening. This is what we can measure thermodynamically, because you're taking a large sample and measuring its magnetic moment. But can we have an understanding what is happening microscopically? Can we write down the microscopic Hamiltonian, do the statistical mechanics, and from that calculate thermodynamic quantities, which shows the same behavior? Not all samples show the same behavior. So these are samples, as we shall understand soon. They are paramagnetic samples. They show a finite value of magnetic moment only if there is a suitably high magnetic field. Why am I using the word suitably high magnetic field? Because it also depends upon temperature. So let's talk about H by T. So only so even because even at a high magnetic field, if you keep on go on increasing the temperature, right, the magnetic moment will again go to zero. So all that of this, can it be explained by a microscopic Hamiltonian? So that using statistical mechanics, if you write down the Hamiltonian, and if the Hamiltonian is correct, the question is, can we predict this thermodynamic behavior? Of course, there can be other kinds of sample as well. And this is discussed again in Rife, but chapter 10. And what has been taken is a ferromagnetic sample. A ferromagnetic sample is something which you could think about to be like iron, right? And here, even in the absence of a magnetic field, yeah, as your experience might have said, even in the absence of a magnetic field, iron can show ferromagnetism. Of course, when you're playing with your iron, I mean, an iron block could be magnetized or unmagnetized, or it can appear unmagnetized. And if you pass a DC current or you stroke it in the same direction via a permanent magnet, then you see that the piece of iron actually, uh, uh, I mean, a piece of iron gets magnetic. That actually happens because there are multiple domains which you might have read about inside that iron sample, and what you are doing is by stroking a iron sample by an external magnet, it's just getting the domains aligned in the same direction. Uh, Right. So basically, each of the domain was already magnetic. I mean, it already had a ferromagnetic, it already had a magnetic moment, intrinsic magnetic moment. And all that you are doing is taking these domains which were pointing in different directions and making them point along the same direction. But here, what we are discussing is uh, even once the system has become magnetized, we're actually talking about the magnetization within a certain domain. We'll talk about this in greater detail in, I think, the next class. But what you do know already, uh, that a magnetic sample at finite temperature in absence of an external magnetic field can show a spontaneous magnetic moment. Okay. And what you are plotting here, this magnetic moment of the sample divided by the maximum magnetic moment which would have been possible for that sample. So this is the maximum magnetic moment of the sample would have been realized at t equal to 0. So that's why it is written m0. So how does the magnetization of the sample change with respect to temperature? It has been normalized with Tc, but I mean, Tc is, if it is normalized by Tc, that means that when temperature reaches the value of Tc, the sample shows zero magnetization. Uh, at lower temperatures, it shows spontaneous magnetization. There's a finite magnetic moment, which is close to 1 at very low temperatures. But as you go above, this magnetic moment gradually keeps on decreasing. And then at a certain value of temperature called the so-called Curie temperature, which you might have heard about, the magnetic moment goes to 0. Can we explain this? What does it mean to explain this? Can we write down the microscopic Hamiltonian and then calculate thermodynamic quantity, suitable thermodynamic quantities? Here, the suitable thermodynamic quantity being the average magnetization or average magnetic moment per spin. And calculate that as a function of temperature, such that we see that, well, it remains nearly constant at relatively low temperatures, and a particular value of temperature, the magnetization becomes zero, and it remains so at higher temperature. So what we say is that the system has become paramagnetic. In the absence of an H field, the sample does not show any spontaneous magnetization. It shows zero magnetization on an average magnetic moment, thermodynamic magnetic moment at temperatures above the so-called Curie temperature. Below the Curie temperature, it shows spontaneous magnetization. Can we understand that? By the way, when we change the temperature, to above the Curie temperature, it doesn't mean that the microscopic Hamiltonian changes. Microscopic Hamiltonian, or the expression of energy for interaction of the microscopic units, assume them to be atoms, again, on which there are certain spins or magnetic moments sitting. The interaction of each of these atoms with its lattice neighbors, suppose they're sitting on a lattice, because we're talking about a solid, really, and it's not only a solid, let's assume that they're a crystal, and you might be reading more about this in the Condensed Matter 1 course, that basically many of these irons and many of these things actually sit in a lattice. Let's assume that. Of course, how lattice comes about is a different question, and that also can be analyzed using methods of statistical mechanics, but today is not the class for that. The point is that, can we write down the microscopic Hamiltonian uh, and get the thermodynamic properties? The point that I was saying, that even if temperature goes above Tc, it doesn't mean that the microscopic Hamiltonian changes. The microscopic Hamiltonian remains the same, but the thermodynamic properties of the average magnetization of the sample, that goes to zero. And the sample, not the Hamiltonian, the sample doesn't show any spontaneous magnetic moment at temperatures above Tc. Can we understand that? Can we guess the microscopic Hamiltonian? And statistical mechanics indeed gives a method, a formalism, such that starting from a microscopic interaction picture, defining different microstates and calculating certain thermodynamic properties, right? And if we happen to plot 1 by chi, and what is chi? Chi is the susceptibility. And what is susceptibility? Susceptibility is if you change the B field, the externally applied B field, by a small amount, how does the magnetic moment change? So it is del M, M being the magnetic moment of the sample. And ideally, we don't like talk about magnetic moment of a sample, because magnetic moment is an extensive quantity. So if you take larger amounts of iron, it will show a larger magnetic moment. So typically, you would talk about magnetic moment per mole, or you will say magnetic moment per gram, or if you are a statistical physicist like me, I am more comfortable about magnetic moment per particle, per atom, per lattice site. And if you multiply it by the total number of lattice points, or the total number of interacting units, or total number of degrees of freedom, number of units which contribute to the magnetic moment, right? So that's how we will talk about it. But let's say, for simplicity, uh, since we are thinking of thermodynamics, let's talk about magnetic moment per mole, and how much this magnetic moment per mole change when you change the B field, okay, as B tends to zero, right? So that's chi. and chi actually can be shown. So you can measure this. You can measure del m del b at different values of temperature, right? And above the Curie temperature, it is seen that 1 by chi, this quantity is changing, is increasing as a straight line with increasing temperature, such units, right? So, so, so it is increasing with temperature, above Curie temperature, but actually, as you take temperature to a certain value, right? Uh, and if you draw a straight line, if you could manage to draw a straight line uh, at t equal to 0, you would still see some finite value of chi, right? Or rather, you would say that 1 by chi equal to t minus tc. Okay, of course, you have extrapolated it to this point, t. So at t equal to 0, 1 by chi, we show the value minus tc. So instead, you can write, because this is an equation of a straight line, and basically 1 by chi equal to 0, which means chi equal to infinity, right, at a certain finite temperature. So when t minus tc, equal to 0, right, so then 1 by chi will be equal to 0, or chi will be nearly infinity. So chi will be nearly infinity as t tends to tc. So okay, I mean, you can understand. I mean, you have you have a qualitative feeling that as you increase temperature, a system loses its magnetism. For a ferromagnetic sample, not all, as you saw previously. But let's take to ferromagnetic samples. So you not only know that ferromagnetic samples above a certain temperature, they lose their spontaneous magnetization, but can you also, from your uh, microscopic interaction Hamiltonian and using the formalism of thermodynamics, also predict that 1 by chi goes as t minus tc, or rather one could say that chi goes as 1 upon t minus tc above the Curie temperature. Can we have a quantitative understanding for this? Can we have a quantitative understanding for a different class of systems which we deem as paramagnetic? So this is the question which we are asking. We are trying to guess the microscopic Hamiltonian, then we'll do statistical mechanics and calculate thermodynamic quantities and try to figure out for which Hamiltonian we can match, what kind of Hamiltonian we can match such experimental data, and for some other systems match this experimental data, and for similar ferromagnetic samples such as this match this experimental data. So this is the uh, name of the game, or this is the game. And of course, we are having this class in 2023, so people have already tried out various Hamiltonians, and I mean, they might have tried out various Hamiltonians, they might have tried different schemes, but today we are going to narrate only the success stories, of course, right? So the things which didn't work, we're not going to discuss, but we're going to build on the 100 years of research and whatever has been successful and reach the books. That is what we are going to teach you. But this is the broad question. When statistical mechanics was developed in the late 1800s, and people were measuring such quantities in 1961 and 1926 even, right? Can you come up with the Hamiltonian which describes such thermodynamic properties and things like this? So with this background, let's start the how the book of Rice in section 6.3 starts. So the phenomena, so just to summarize before we go into the mathematics, let me tell you the brief answer. A priori, the questions were this, the questions are motivated by this, but I'll just tell you the answer in brief and try to develop understanding, a qualitative understanding of what is the phenomena, and then we'll do the mathematics, right? The mathematics is that of calculation of particle function, the free energy, and so on. So what you have in the paramagnetic sample, the paramagnetic samples are those samples which do not show any spontaneous magnetic moment, but they show some alignment of spins. Okay, so they show that the sample shows finite values of magnetic moment on application of an external magnetic field, uh, and as you go on increasing the magnetic field, the magnetic moment saturates at very high magnetic fields. But of course, again, if you increase the temperature, then again you see that the magnetic moment disappears. And what we understand today is, suppose this is the lattice of a solid of a paramagnetic sample, and at different points in space you have various atoms sitting there, which have their own intrinsic magnetic moment. And with the paramagnetic sample, the the magnetic moment is sitting at different lattice sites, they do not interact with each other. So they are just independent magnetic moments. They are sitting, so there are atoms, there are electrons, there are nucleus, and so on and so forth. At each lattice site, you have a finite magnetic moment, and one atom is not interacting magnetically with its neighboring atoms. Why do I stress the word magnetically? Of course, this atom is interacting with its neighbors, right? Else you wouldn't have the lattice. Else this system of atoms, molecules, whatever be they, sitting on a lattice, they would fly around in space, right? So the Hamiltonian of the system, of the full system, is of course the kinetic energy of each of the atoms plus different kinds of interaction energy with electron interactions and so on and so forth. There would be electron nuclear reaction interactions as well. Within nucleus there might be interactions as well, but in addition to all this, there would also be energy or interaction energy due to spin degrees of freedom sitting at each lattice point. So what we're going to do is focus on only on the energy due to the spin degrees of freedom. And of course, there are other kinetic energy terms and other interaction terms between the atoms sitting at different lattice points, which essentially keep the lattice in space. So we are not going to discuss this. The Hamiltonian, the part of the Hamiltonian which we are going to discuss is related to whether at each lattice point there's a magnetic moment or not, and if they are interacting with the next nearest neighbor or not. And for paramagnetic sample, what you have is at each lattice point you do have a magnetic moment, but it does not, the magnetic moment at one site has no interaction with the magnetic moment of the next site. Suppose this is site number 2 and this is site number 1. And then similarly, the magnetic moment here is not interacting with the magnetic moment with this. This magnetic moment is not interacting with the magnetic moment of its neighbors, and so on and so forth. And if you have such a system, as I shall show, those systems are paramagnetic samples. Okay, so spins are not interacting with its neighbors. Non-interacting spin systems are essentially show characteristics of paramagnetic samples corresponding to such systems. And why is it so? We shall understand soon. Okay. Uh, and as we shall show, so we are not considering these terms. So these terms are there in the full term of the Hamiltonian. We are discussing only this term of the Hamiltonian, energy due to interaction of spin degrees of freedom. Okay. So now suppose you have this sample. This sample is sitting in contact with air, let's say air or liquid. So the air or the liquid is essentially acts like a heat bath of the statistical physics, right? And these spin magnetic moments. So I shall use the word magnetic moment and spin interchangeably, because once you know the spin at each lattice site, then you multiply it suitably by the Bohr magneton and the Landis factor, and then you know the maximum magnetic moment which is sitting on each of these lattice sites, right? Now, each of these lattice sites, the spins can absorb, or more accurately, exchange energy from the lattice and thereby be in thermal equilibrium. So what it means is, so what in statistical physics we are discussing is, we are not discussing how each of these atoms, each of these magnetic moments exchanges energy with the heat bath, right? So heat bath is all around us. It could as well be that there is a lattice here. This lattice is being hit around by gas molecules. The lattice itself is exchanging energy uh, from the environment, and thereby this entire lattice is at a certain temperature, and then this magnetic moment can absorb heat from the lattice, or maybe directly by being hit by the gas molecules. We are not discussing the mechanism, the microscopic mechanism of heat exchange, which, or energy transfer, heat exchange or energy transfer, which will be more a topic of the quantum mechanics 2 course. But here we say that suppose there's a method by which each of these atoms can absorb or release energy to the environment. So the sample as a whole, each magnetic moment does so, the sample as a whole exchanges some amount of heat or energy with the environment. What would be the behavior in terms of the magnetic moment of the sample? So this is the question which we are asking. We are not discussing the mechanism of energy transfer, but suppose there is, and the sample can absorb a certain amount of energy, heat from the environment or release it, then how would the sample behave? So that's the question. So qualitative analysis. Now, if there is a magnetic moment sitting on at each lattice site, then the Hamiltonian of interaction related to the spin degrees of freedom. Of course, there are other degrees of freedom as we discussed here. We're not discussing here, we're discussing only this. The energy of interaction, the Hamiltonian of the magnetic moment, right? Interacting with an external magnetic field. So B is the externally applied magnetic field. Suppose it is pointing in this direction. Let's call that Z. Then the energy of interaction is minus mu dot B. Like this, if there's a magnetic moment, it will try to align itself with the direction of the magnetic field. So we are specifying this magnetic moment, but this magnetic moment at each lattice site can be written in terms of the Bohr magneton, the Landis factor, and the spin quantum number, the maximum spin quantum number. Now let's, for simplicity, assume that the magnetic moment is quantized. The spin can be only plus half, or minus half. Now, if the spin points in the direction of the magnetic field, so that's how you break the degeneracy. So suppose the spin points in the direction of the magnetic field. This is the direction of the magnetic field. Let's call that Z. Then the energy gained by the atom, the lattice unit, is minus mu dot B, because mu is pointing in the direction of B. So this is a positive quantity, and the Hamiltonian comes with a minus sign. So the magnetic moment has aligned with the magnetic moment has aligned with the direction of the external magnetic field, and thereby its energy is decreased. So it's happy sitting here. But in the thermodynamics, in a statistical sample, this spin can also absorb energy from its environment and go to a higher energy state, microstate. Of course, the microstate is defined by all the n atoms, but we're going to focus on one spin, and we'll say that each of these atoms or lattice points are behaving the same way. So each lattice point, since they're non-interacting with its neighbors, can also absorb some amount of energy. How much energy? Mu b minus mu b. So 2 mu b. So if it can absorb that amount of energy, then it can also flip its spin and point in the opposite direction. And in that case, the energy of that particular lattice site will have an excess energy of mu b. So the energy difference is 2 mu b, but the energy is plus mu b. Here the energy of that magnetic moment is minus mu b. So there are two different microstates with different energy, right? Now, if so the question is, what is the probability that the magnetic moment will be in this microstate? Of course, there are n other atoms, and that will define the microstate. But let's talk about the microstate of this particular magnetic moment. So what is the probability that this magnetic moment will be pointing down or up? Up being the direction of the magnetic field. So the probability that the magnetic moment will point down is e to the power minus E1, the energy, by kBt, and this energy is plus mu b. So this mu b by kBt by z, right? So here I've missed the z factor, but there should be a 1 by z. And similarly, the probability that the system or the magnetic moment will point in this opposite direction is, so this should be proportional to, or write 1 by z, is e to the power minus E2, and E2 is minus mu b. So hence it's e to the power mu b by kBt into 1 by z. Of course, z is a certain normalization factor. So z is not going to change depending upon whether the magnetic moment is up or down. So that's by a constant factor, right? And the energy changes to mu b. Now suppose mu b, the magnetic field, mu into b, the magnetic field, this is an unit of energy, kBt is a unit of energy, was much larger than kBt. So mu b is much larger than kBt. So the factor in the what is it called, exponent, is much larger than 1. I mean, yeah. So e to the power mu b by kBt is a large quantity. On the other hand, e to the power minus mu b by kBt is nearly e to the power a very small quantity. So it's e to the power 0, right? It's close to 0, and this is so basically this. So of course it has to be multiplied by z to get the probability. So the probability of pointing up will be very large, right, as compared to the probability of pointing down, because this quantity is much larger than this quantity. So this probability, when you divide it suitably by z, is much larger than this quantity, which means that if mu b by kBt is high, KBT is much lower in value, it has a low value as compared to mu B, right? Then an individual spin would, with a very high probability, point the same direction of B. And that is true for each of the magnetic moments sitting at different lattice points. So all of them would like to point in the same direction and in the direction of B. So you have many of magnetic moments pointing upwards. As a consequence, in the sample, you will see a very large magnetic moment of the sample, right? So basically, if you now look at this picture, at a high magnetic field, large number of magnetic moments are pointing in the same direction, right? All of them are, nearly all of them are pointing in the same direction. And even if you increase B, there is not possible, it's not possible that there are more magnetic moments which are pointing in the same direction. I mean, very slight change can be possible, let's assume. So most of them, 99.9%, are pointing in the upwards direction. So even if you increase the magnetic field, it's not possible that more magnetic moments will start pointing in the same direction of B, or very small number can. So magnetic moment has saturated. So if you have a microscopic picture, right, where you have non-interacting magnetic particles and an application of an external magnetic field, such that the energy of mu B is much greater than KBT, then all the spins are pointing in the same direction. And hence you have a saturation in the magnetic moment, which is in tune, which is seen graphically. What would happen if keeping mu B the same? We keep on increasing KBT. At some point, of course, mu B and KBT will be in the same order of magnitude, but let's talk about the two extreme cases. So when KBT is much higher than mu B, right? If KBT is much higher, such that this quantity is a very small quantity, and similarly this quantity is a very small quantity, then the probability this quantity can be written as e to the power, so of course there's a 1 by z here, this 1 by z is sitting there, but this can be written as 1 plus x, I mean mu b by kbt is, let's call it x. So it's 1 plus x, and this is an extremely small quantity. And similarly, this will be a quantity 1 minus x, right? And this quantity can be sorry, but this can be 1 minus x, and this can be 1 plus x, right, into 1 by z. X is a small quantities. It's basically close to 1 by z for this state and 1 by z for this state. What does it mean? It means the probability of pointing up and pointing down are different. One is 1 minus x, one is 1 plus x, but by a relatively small amount. The probability of pointing up and down is nearly the same, not exactly the same, but nearly the same. So at very high temperatures, you have equal number of spins pointing up and an equal number of spins pointing down. As a consequence of which, you have equal number of up spins and down spins, slight difference. And the net magnetic moment that you see is nearly zero. Okay? So this point is, if you keep the h same and keep on increasing t, which is in the denominator, that has increased a lot. So h by t is nearly zero. So at very high temperatures, you see magnetic moment to be nearly zero, right? And that is exactly what we have been, what you see in this graph, right? So non-interacting magnetic spins seems to be pretty good, and especially if you use this probabilistic picture, seems to be a pretty reasonable way of describing paramagnetism. So this we talked about qualitative analysis in terms of intuition and so on and so forth. So this is what we already discussed. E1 by kBt will be nearly 0 or 1 minus x and 1. I mean, these quantities are relatively small, and hence you can expand your exponentials as 1 plus x or 1 minus x, and the probability is nearly this is the same, and you have equal number of spins. I mean, if you look at a particular spin, I mean, it has high probability of also pointing down. So if you look at n spins, there are nearly an equal number of spins pointing up and down, slight difference, and the net magnetic moment that you see is really very close to zero. Note, the system is constantly exchanging energy. System. Of course, as you increase temperature, the fluctuations will also change. And this is the basic summary. So let's do the mathematics in the next recording.